Hello everybody, welcome back. Day 19, Titrations. And just so we know that on the Chem 152 final exam, everyone, there is two questions. One question will be a strong titration, and another question will be a strong, weak titration. They will be on the final every semester. So I would highly encourage you to know how to do these for the test. So first, let's define a titration. And this is a method of quantitative chemical analysis. To determine the concentration of an analyte. Well, let's determine what an analyte is. We'll define an analyte, we'll define a titrant, and then we'll talk about this. The analyte is the unknown and in the flask or beaker. The analyte's the unknown. The titrant is of known concentration in the burette. So it's a method. What's a method? So some process we're going to use to quantify, give numbers to this, and we're going to analyze this chemical. So it's a method to analyze this chemical quantitatively with numbers, not just qualitatively, like describing its color or clarity or how big it is. None of those physical characteristics. We're actually talking about how much sodium hydroxide is in this container, how much of anything is in this container. The analyte then will be down here. In a beaker. So I have a ring stand. A burette clamp. And then the burette. In this case, this is a beaker. Could be a flask too. And the titrant is in here. In this burette. And that's known. Now, there's two more things that we want to define. One is standardization. And this is the process which I check the concentration of the titrant. So we're going to say with a known analyte, we check or verify the concentration of titrant. We do that to make sure that what we made in the burette is accurate. And so you probably have done this in a lab setting. Maybe you haven't. And so let's explain it. you're going to make traditionally in a Chem 1, Chem 2 lab, you're going to make a sodium hydroxide solution, maybe a 0.1 molar. So you'll take maybe 4 grams of sodium hydroxide or 2 grams of sodium hydroxide and put it into either 1 liter or half a liter, depending on if you're making a whole liter or half a liter. In my labs, it would be 2 grams of sodium hydroxide and 500 milliliters of water in a volumetric flask, and we make our solution, our sodium 0.1 molar sodium hydroxide. Wonderful. We have to check to make sure that it's actually 0.1 molar. Why? Well, volume is temperature dependent. And so if we make it one day and we use it another day, it could be off a little bit. That could happen. Now we're pretty much climate controlled. We're pretty good in the lab, but there are days where it might be 5-10 degrees warmer or cooler. Well, you want to recheck. Always want to recheck. And so our analyte that we use to determine what our concentration of sodium hydroxide is, the analyte down here that we would know for our standardization process, we use KHP, which is potassium hydrogen pentylate, which is a solid. So we use a mass of that KHP to determine the concentration of the sodium hydroxide. Masses are easier and more accurate to measure than volumes. Why? Well, masses do not change with temperature. So you might have a perfect volume, your eye level is perfect, it's within 0.00001 milliliters of what it should be, and then it's 2 degrees warmer. Now it's off. So that's why we use the mass to do this, and you have to do it each time you use it technically. There's another point now when we talk about titration that we really care about, and that is the equivalence point. And this is where, when the moles of analyte equal the moles of titrant. So the equivalence point when the moles of analyte whenever our analyte is equal the moles of the titrant. That is a very important point because we want to know, if we want to know how many moles of analyte there are, we can measure on this burette. There are graduations, so to speak, and it's pretty accurate. And we can read how much we delivered. Like we usually start, it's usually at 0 up top, 0.00 milliliters, and the ones we have in our lab go to 50 milliliters, and that tells you how much was delivered, which is wonderful. That way we can figure out where our analyte is. The only problem is, because we're going to dive into acid-base chemistry here, acid-base titrations. Acids, like vinegar, hydrochloric acid, a lot of the acids we use in solution, and especially a dilute solution, are clear and colorless. The bases that we're going to use, typically sodium hydroxide, in 0.1 molar solution, is clear and colorless. So how do I know when I'm done? That question's answered by using an indicator. The one we use in lab is phenolphthalein because it's just what we would use. But this changes color because phenolphthalein changes color around pH 8, and that's what we want in our lab. But not every titration uses phenolphthalein. There's a bunch of them. It changes color at a certain pH or other, I'm just going to say other concentration. And the reason we're saying other concentration, because there's redox titrations. We actually use some in Chem 1 here at Coastal that we use iodine. We got I- to I2 with starch. That's a common one as well. And there's a clear to purple color change going on. But this is but for our purposes, for acid base, I'm going to write down acid base, right? The indicator is a weak acid that has a different color in solution than its conjugate base. And so that's how we will look at the titration, and so how we know when it's done, so to speak. Now, when it's done isn't necessarily the equivalence point. We always go past the equivalence point. Oh, try that again. Oh, here we go. Perfect. So we talk pH on the y-axis, and on the x-axis would be volume added of our titrant. We'll have the initial pH value of the analyte. Let's call it there, right there. That's the initial pH of analyte. So in this case, I'm going to have an acid, because if pH 7 is right there, let's call that pH 7. pH 0, that's pH 14 there. We're going to have an acid. It's acidic. What's going to happen is, as we add our titrant, we're going to slowly go up, and then it's going to explode up and go. Right there is our equivalence point. And that's, of course, this is only for a strong. We'll get to that later. So that's the equivalence point. We have a couple regions here. So I have the initial. That's the initial. We have blue for before. We have before equivalence. I'll have equivalence. And then we'll have after equivalence, past equivalence. And those are the 4 regions that we're talking about, the 4 spots. Now, the equivalence is not always at 7. Strong it is, strong weak it's not. But that's the general characteristics. And I just want to point some out. A lot of times, from around somewhere in here, that dotted line, to somewhere in there, that could be 1 or 2 drops of titrant. So it's not a big amount. Not a big amount at all. Now, if I have a base in the burette, so let's draw the difference. So let me come back here. And so in this situation, I have acid in a flask or beaker and base in burette. Down here, we're going to have acid in burette, which would be the titrant, and base in flask or beaker, the analyte. So we're going to have a little bit different looking graph. Let's try to draw that again. That's my axes. So again, we're going to have pH, and we'll have volume added. This time, the initial will be up here. And it's going to look something like this, where my equivalence point would be there. As you see, it's the mirror image. That'd be the volume added, and there's your equivalence point. So again, we have the same regions. I have my initial, I have before equivalence, I have equivalence, and I have past equivalence. Same for regions. Now this is a limit here, right? Just like it's a limit up here. And so if I have 0.1 molar sodium hydroxide, that pH of 0.1 molar sodium hydroxide is 13. So eventually I can get to a pH of 13 for this titration. I probably won't get there. I'll approach 13. So 12.8, 12.7, 12.6. I'm not going to get any higher because I'm just not for a long time. Same one down here. If I have 0.1 molar HCl, 1's my limit. So I'm going to get close to 1, but I'm not going to get to 1. Now let's do some examples. Let's do a strong titration. Now in this strong titration, I have a couple things. So there's let's draw the ring stand. Draw the burette clamp here. Perfect. Draw my burette. And we'll draw a flask. We have 40 milliliters, 0.1 molar HCl titrated with 0.1 molar sodium hydroxide. So my sodium hydroxide is going to be up here in the burette, and my acid will be down here. We have 40 milliliters, 0.1 molar HCl. I didn't write down all my sig figs, so that was bad. Let's rewrite that. 40.0 milliliters, 0.10 molar HCl. And we have 0.10 molar NaOH. So in this example and the next one, because the next one will be a strong weak, we're going to have the same very easy math. So you can see the points. So now there's 4 points. There's the initial. I'll try to do them the same color as the previous. The before equivalence. Equivalence. No, equivalence was green, wasn't it? Equivalence, before equivalence, and past equivalence. So for part one. Well, before we even do part one, let's talk about the what's the reaction? What is the balanced equation? HCl, NaOH, so hydrochloric acid, sodium hydroxide, going to, we have what? Switch dance partners, NaCl, and H2O liquid. Well, what's the detailed ionic equation? H plus Cl minus, Na plus, OH minus. Hopefully this is very familiar. Na plus, Cl minus. Right, we're doing detailed ionic equation from Chem 1. That's where you would review in Chem 1. Your Chem 1 notes. Well, what do we know? We have our net ionic equation would be H plus aqueous plus OH minus aqueous going to water. That's great. One nice thing about this, though, right here, this guy, because it's strong, there is no hydrolysis. And that's a big, fat smiley face, because that makes our lives a lot easier. And in the next example, you'll see why. So now we can go to the initial pH for number 1. Number 1, the initial. I have a strong acid. So the concentration of HCl is the concentration of H+. And the pH is negative log of H plus or H3O plus. So pH equals negative log. That concentration is 0.1 molar. So the pH is 1. Oh, it's not highlighted. Why is it not highlighted? There we go. There we go. pH is 1. Wonderful. So there it is. So that's before any reaction. That's before the burette is opened and any sodium hydroxide goes into the flask or beaker. Next, part 2. Well, let's look at our concentrations. We'll do our reaction. H plus aqueous plus hydroxide going to H2O liquid. We know we have 40 for D milliliters and 0.10 molar. And I have 0.10 molar, but I only have 20 milliliters. Well, one thing to note here, we have a new volume of 60 milliliters. That's going to be important. Okay, so let's look. I have 40 milliliters HCl times, for every 1,000 milliliters, 0.10 moles. So that's going to give me 0.004 moles H plus, or 4 millimoles, if you want to use millimoles, if you're good with that. If you're not, don't. 20 milliliters of NaOH. Same thing, for every 1,000 milliliters of sodium hydroxide, I have 0.10 moles. That gives me 0.002 moles of hydroxide, or 2 millimoles. Why would I use millimoles? Because moles per liter is concentration. If I divide by the top by 1,000, I get millimoles. If I divide the bottom by 1,000, I get milliliters. Moles over millimoles over milliliters is also molarity. So that's why you don't have to use that. In fact, I won't do that for you. But you can. If you're good with the math, feel free to do that. Makes your numbers a little cleaner. We have 0.004 moles of H plus, or 4 millimoles, and 0.002 moles of hydroxide. Well, if you notice, we are, in this case, halfway to equivalence. We're halfway. So I'm going to do an ice table. ICE. We know my limiting reactant would be our base, our hydroxide, minus 0.002, minus 0.002, and we don't care about water because it's not going to change. It does change, the volume changes, but the concentration of water is relatively constant. So at the end here, I have 0.002 moles of H plus and nothing of hydroxide. So that gives me 0.002 moles. I have 60 milliliters, or 0.0600 liters. So that means my concentration of H plus is 0.03 repeating molar. I could have used 2 millimoles over 60 milliliters too. Either way works. The pH is negative log of H plus. pH is negative log of 0.03 repeating, which is 1.48 or 1.5, and that would be halfway. So we're halfway. We're halfway to the equivalence point, and our pH is only 1.48. It started at 1, and we're only at 1.48. This is a good reminder. This is exponential. This is why it's different than a linear. It's an exponential. Part 3. And as you can guess, so part 2 was before equivalence. Part 3 is going to be equivalence. So let's talk about part 3. I got H plus, OH minus, going to H2O. We have 0.0, well, I'll write it all out for us. 40.0 milliliters and 0.10 molar. So we know that's 0.004 moles. Now my base, OH minus, we have 40.0 milliliters and 0.10 moles, molarity. And same math as right there in orange. Right, 40 times 0.1 over 1,000 is 0.004 moles. Well, they're both there. And so if we did an ice table, minus 0.004, minus 0.004, none and none, so that the concentration H plus is equal to the concentration OH minus. So the pH is 7. So strong, strong equivalence, the pH is 7. So this is always for strong, strong. That's nice. 7.0. I'll put the 0.0 down. Part 4 now is past equivalence. If you notice, I'm always going back to the original conditions. I'm not carrying on. And why would I do that? The answer lies in, what if I make a silly mistake? 0.004 minus 0.004 is 0.008. We've done stuff like that, especially panicked on a test, right? Especially if you have test anxiety. That's not out of the realm of possibility. 2 times 3, I've done it as 5 before and laughed about it later, but we've done it. So I always go back to the original conditions in case there is an issue with my math or I transpose numbers in a calculator. Very easy to do. I miss a 0 when I'm typing fast in the calculator and I miss a 0. I always go back to the original conditions so that way my mistake doesn't make, in a previous part, doesn't make the next part wrong. So our stuff now is 40.0 milliliters H plus at 0.10 molar, which is 0.004 moles. We now have 60 milliliters of base being added at 0.10 molar. So 60 milliliters times, for every 1,000 milliliters, there is 0.10 moles, 0.006 moles, or 6 millimoles. Note, Oh, I don't want to highlight. I want to use this one. Our new volume of the container would be 100 milliliters. 100 milliliters. So let's see what we have here. ICE. What's the, looks like 0.004 is our limiting reactant, our H+. So we have no H+, but we have 0.002 moles of hydroxide. Our new volume was 60, and so we're going to bring this up here. I'll bring this up, bring that down. 0.002 moles. 100 milliliters, the same thing as 0.1000 liters. So that gives me 0.020 molar OH minus. Well, how do I do the pH? Well, remember, pH plus POH is 14. Right? And the POH is the negative log of hydroxide. So the pH would equal 14 minus the POH. So the pH would equal 14 minus the negative log of 0.020. So our pH would be 12.3 in this case. And there we are. The graph of this, if we were to graph this, the graph of this, if I have pH, which volume added in milliliters, we would start off at 1, the pH of 1. We go up to pH of 7 and go pretty much up to pH of, well, let's say that's 12, not to scale. We'd start off and go something like this. No, I don't like that. Just something like that. Maybe. So there's my equivalence. There's 20 milliliters, 40 milliliters, same distance, 60 milliliters. Something like that would be our graph. Strong, weak titration. So now we have 40 milliliters, 0.1 molar acetic acid with 0.1 molar NaOH. So again, if I were to draw this out, my acetic acid's down here, my base is up there. So this is 0.10 molar NaOH and 0.10 molar 40.0 milliliters of acetic acid. Okay, so the initial is before. So part one here is before NaOH is added. So 0, nothing. I have 0.10 molar C3COOH. The volume doesn't really matter. It's 40 milliliters, but it's just a weak acid. So we do a nice table. The thing we don't have on this sheet is Ka, and Ka is 1.8 times 10 to negative 5. We've done this before, so let's write our Ka expression, our reaction for Ka, and then the expression CH3COOH aqueous, water, hydronium H3O plus AQ. My expression for Ka would be hydronium acetate all over acetic acid. Okay, ice table. The ice table would be 0.10 molar, don't care, none, and none. Minus x, plus x, plus x. We have 0.10 minus x, x, and x. So plug it into Ka. 1.8 times 10 to the negative fifth equals x squared all over 0.10 minus x. Can we approximate here? The answer is yes. If I approximate, I can make this 0. I can approximate that to 0. So we get 1.8 times 10 to negative 5 equals x squared over 0.10. Do the math, bring the 0.1 up. I get 1.8 times 10 to negative 6 equals x squared. Square root both sides. X, which would equal H3O plus in this case, would be 0.0013. So then the pH negative log, of course, of H3O plus or H plus. So our pH would be equal to the negative log of 0.0013, and so that would be 2.87. Oh, that's weird, 7. 2.87. So that is the initial pH of our solution. Part 2, we have to talk about the equation. So CH3COOH, acetic acid, with sodium hydroxide, going to NaCH3COO and water. Well, first, what's the net ionic equation? Well, acetic acid stays together in solution for the most part because it's a weak electrolyte. Some of it dissociates, but most of it stays together. Sodium obviously splits apart from hydroxide. Strong electrolyte, ionic and aqueous, strong base. Sodium and acetate split, same reason. And water stays together. So my net ionic reaction, my complete ionic reaction, is acetic acid plus hydroxide going to acetate and water. It's the same math as before. So we have our acid, if we go back to our acid, I have 40 milliliters. I'll write that down, 40.0 milliliters and 0.10 molar. So 40 milliliters times, for every 1,000 milliliters, I have 0.10 moles. That's 0.0040 moles of acetic acid. Hydroxide, sodium hydroxide, I have 20 milliliters, 0.10 molar, and the same thing, 20 times 1,000 over 0.10, 0.0020 moles. Now there's a big difference in this one, and I'm going to draw it as a sad face because it's hydrolysis. And that's going to complicate things soon. Also, there is a new volume here. So we're taking our 40 milliliters plus our 20 milliliters, 60 milliliters. All right, ice table. Well, we have 0.002. So at equilibrium, I end up with 0.0020 moles of acetic acid, no moles of conjugate of hydroxide of base, and I end up with 0.00220 actually moles of conjugate base, acetate. Well, since I have acid and conjugate base in solution, right, technically speaking, we should get the molarity. So let's get the molarity of both. 0.0020 divided by 60 milliliters is 0.0600 liters, correct? Yes. So 0.0060. Nope, I got an extra 0.060 liters, moles. And that's for both of them. So 0.002 moles of my acid and my conjugate base give me 0.03, repeating, so there's two sig figs there, molar CH3COOH and 0.03 molar, repeating, CH3COO minus acetate. Because I have both acid and base in solution, we are in a buffer. Right, this would be a buffer because I have acid and conjugate base. So that means I can use the Henderson-Hasselbalch equation, pH equals pKa plus the log of concentration of base over the concentration of acid. So pH equals pKa, which would, in this case, negative log of Ka, which is 1.8 times 10 negative 5, plus the log of base, 0.03 repeating, over acid, 0.03 repeating. Well, 0.03 over 0.03 is 1. The log of 1 happens to be 0. So halfway, I don't want to use orange, halfway to equivalence, pH equals pKa for a weak, strong, weak titration. In this case, the pH is 4.74 because that's what pKa is. So anytime we're before the equivalence point from strong, weak, we can use this Henderson-Hasselbalch equation to get the pH. And halfway to the pH, to the equivalence points, the pH is the pKa. Now we have equivalence. So for equivalence, I have reaction again, CH3COOH plus hydroxide going to CH3COO minus acetate and water. We have 0.0, well, let's write everything out. 40.0 milliliters and 0.10 molar. So that gives me 0.0040 moles of acetic acid. Now we have 40 milliliters at equivalence point and 0.10 molar. So I also have 0.004 moles of base. Wonderful. Ice table. Because it's so easy to forget this conjugate base here. Minus 0.004 minus 0.004 plus 0.004. So no acid, no base, but we end up with 0.0040 moles of acetate. The new volume, 40 and 40. So the new volume is 80 milliliters. So if I divide that by 0.0800 liters, that ends up with 0.050? 0.050 molar acetate. Okay. Well, that's a base. So we have CH3COO minus plus water. Oh, that was a weird arrow there. Going to CH3COOH and because of hydrolysis at the equivalence point, we're adding base back to our mixture. So the moles of acetic acid and the moles of sodium hydroxide are equal. However, the pH is not going to reflect that it's 7 because our conjugate base is going to add more hydroxide to the mixture. So let's calculate how much hydroxide it adds. We know that I have 0.050 molar. Doesn't matter. None and none. Minus x plus x plus x. 0.050 minus x, x and x. Excellent. What is KB? KB is, well, if you remember, Ka times KB is Kw. KB, so let's write that down. Ka times KB is Kw. Well, KB would be Kw over Ka, which would be 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5. And so KB happens to be 5.6 times 10 to the negative 10th. The KB expression happens to be acetic acid, hydroxide over acetate. So let's throw in our numbers. 5.6 times 10 to the negative 10th equals x squared all over 0.050 minus x. Good news, we can approximate because this is more, that's 5 times 10 to the negative 2, and that's 5 times 10 to the negative 10. That's 8 orders of magnitude away. We only need 3, so that's good. So when we approximate, this is 5.6 times 10 to the negative 10 equals x squared all over 0.050. We do some more math here. Bring the 0.5 up. I get 2.8 times 10 to the negative 11th equals x squared. X, which equals my hydroxide concentration, is 5.3 times 10 to the negative 6 molar. That's square root of both sides. So the pH is equal to 14 minus the pOH, just like last time. pH is 14 minus the negative log of 5.3 times 10 to the negative 6. So the pH happens to be 8.72. And so it's a whole, almost 2 orders of magnitude higher sodium hydroxide concentration than neutral. So that's the equivalence point. Then we have, last but not least, so past equivalence, we have 60 milliliters of 0.10 molar NaOH. 60 times 1,000 over 0.1 over 1,000 would be 0.006 moles. Writing our balanced equation, we have acetic acid, hydroxide, acetate, and water. So initially we have 0.0040 moles of our acetic acid, and as we just calculated, 0.0060 moles of hydroxide. Ice table. It's easy to forget the conjugate bases involved here. Minus 0.004 minus 0.004 plus 0.004, and it's technically 0 because there's 2 sig figs there. And so we have no acid. We actually end up with 0.0020 moles of hydroxide and 0.0040 moles of conjugate base. The new volume, so we had the original 40 milliliters and the 60, it's the same 100 milliliter total volume, or 0.1000 liters. And we divide by 0.1000 liters for both of these. We're going to end up with 0.02 molar hydroxide and 0.040 molar acetate. Well, now we have acetate in solution again, and that's altering the pH. However, if we assume that 0.04 and 0.05 are the same, which they're not, 0.05 molar acetate produced a hydroxide ion concentration of 5.3 times 10 to the negative 6 molar. So we're going to say, let's say 0.04 produces the exact same number, 5.3 times 10 to the negative 6. It doesn't. It's less, but let's just say it does. What's 0.02 plus 5.3 times 10 to the negative 6 molar? 0.02. So at this point, we can ignore hydrolysis because the concentration of hydroxide that the hydrolysis produces is so much less than the concentration of hydroxide from the burette, from sodium hydroxide. So the pH is equal to 14 minus the pOH, or 14 minus the negative log of 0.02. So the pH ends up being 12.3, just like it was in the other one, in the other strong. Down here, 12.3. Drawing the graph. pH volume of NaOH added in milliliters. So we had the initial pH around 2.87, about 3 almost. So right there, I'm going to say that's 2.87. That's the initial. And then it slowly rises a little bit, and then it's kind of like that. That's too much of a slope. And then there's a very sharp uprise and leveling off. There should be a slope of 0 there. It should be a vertical line. That's my equivalence. And that would be right there at 40 milliliters. So there's 60 milliliters. And that pH was 12.3. That was 8.7. And then we have right here at 20 milliliters, that's 4.74. And right there. And we have what we call this region right here on this chart. It's a little bit different. My graph is not as nice, maybe as your book's picture. This is the buffer region, where the pH didn't change much. So that's a strong weak example. Now I do have a polyprotic that I keep flipping to, and a polyprotic is very similar to a regular titration, except there's 2 equivalence points. And the first equivalence point is half the volume of the second equivalence point. We don't do much with this, but it's there. So let's recap. Let's recap this. And so if we look at a titration, there's what we're going to call the fraction titrated. We'll have a strong, strong, and strong, weak. So the initial fraction titrated. Right, the pH, right, is due to the concentration of strong, I could spell, acid or strong base. And for the strong weak, we got to use the ice table and K. Whether it's a Ka or Kb, doesn't matter. It's just whatever K. Then we have, before the equivalence point, we'll have 1/4, 1/2, 3/4. Then we'll have equivalence. And we'll have past equivalence. And all before equivalence here, the pH is due to excess analyte in flask or beaker. Whereas for strong weak, at 1/2, it's pH equals pKa, and we can use the Henderson-Hasselbalch equation here. At equivalence, the pH of a strong, strong is going to be 7. For the strong weak, the pH is due to hydrolysis of the conjugate. Past equivalence, we have the pH. For both of these, the pH is due to excess titrant from burette. So they're the same there. Draw some lines here, make it a nice little chart. There we go. So there's a summary of titrations. And just so we know, the fraction titrated for equivalence would be 1. And the past equivalence, a lot of times we'll go to 1 1/4. Doesn't necessarily have to be 1 1/4, but that's where it'll go to. So that's titrations. Hopefully that worked. Take care, guys. See you next time.